Hi everyone, welcome. Thank you for joining high voltage seminar this year. Today I'm going to talk about the designing titanium grade efficiency into GaN-based power supplies. My name is Pengkun Liu. I'm the apps manager here on TI GaN's team. So I also want to thank the contributors to this presentation materials, including our apps engineer, John Gomez, Chi Xu, and also TI Power Design Service Shenyang Yu's team. During the presentation, if you have any question, feel free to use the QSN block on this page, and we will answer your question real time or later in the live Q&A sessions. So let's see the agenda today. Today I will start with the introduction of the solar PFCU platform, this and the equipment, and what is titanium grade, and then PFCU itself is a huge topic. It's definitely very hard to talk about every details in this large system. So today I will narrow down to the efficiency performance of different topologies in two major parts there: the AC/DC topology stage and the auxiliary power supply stage. Through some of the case study, let me have a cursor here. So through some of the case study, I'm going to show why you need GaN there to meet this titanium grade efficiency requirement, and also some cost comparison between the proposed solution and the previous solution. Okay, yeah, let's start with the general introduction of power supply unit. So power supply unit, or in short PSU, is an internal IT hardware that converts the grid AC power to DC power for the server. The AC is like the grid voltage, and the DC depends on different structure of the PSU. The output can vary. Normally, you can see from this entire power conversion, there are normally two stages. One is from AC to a DC mid voltage DC link, and then from this DC link to the end DC voltage you need. So one AC/DC stage, another is DC stage. On top of these two, you also need the power supply, auxiliary power supply for all the devices in these two stages. So that's auxiliary power stage outside there. So for the AC/DC stage side, this is some requirement from the government, like they mandate the use of a power corrector stage in the AC/DC supply, just in order to facilitate clean power draw from the grid. PFC, the purpose of the PFC is it can shape the AC input current to follow the same shape as the AC input voltage, which can maximize the real power drain from the grid, making like the electrical equipment appear like a pure resistor with zero reactive power. And on the other side, the DC/DC stage is to convert this link voltage to the voltage you want. Normally, the topology is LLC or phase shift full bridge, this kind of soft switching topology, so that the efficiency target can be met. So based on the different structure, there are normally two different type of power supply units. One is like the ITE level, meaning this is a traditional like information technology equipment level. So basically, it's for each of the end server unit, it will have one power supply to it. So the output of this kind of PSU is normally 12 volt. And there's another one where another different structure is the power supply unit will provide the power for the entire rack. And normally that kind of output is 48 volts, so that conduction loss, the current can be minimized, and the conduction loss can be minimized as well. This is conduction loss on the wire, copper wire, and this kind of things. So for the PSU designs, there's always like two direction. Like we want the PSU to be more effective and also smaller, like basically have higher power density. On the efficiency side, let's talk about efficiency side. This is our major topic today. So on the efficiency side, 80 plus, this 80 plus standard is a voluntary certification program for these power supply units about their efficiency. You can see from year to year, I think this is established like 2004 or something. And from year to year, as the technology and design grows, the grade has been changed from standard to bronze to silver, and all the way to the titanium grade we are talking about these days. Considering the operation profile of PSU, the most important efficiency point is actually at half load. So ideally, we should design the PSU, meaning choosing the right device adjacent, selecting the right inductor, and so on, to have the peak efficiency happening at half load of the converter, like 50% load. With titanium grade, the PSU are shooting for more than 96.5% overall efficiency at this point for all the IT level PSUs. And also for the rank level, this kind of requirement is even higher, with like more than 97.5 at half load. On the other hand, power density requirement is getting, more and more strict as this is as well. For the IT level, considering the power level is small, and so it is smaller, is like less than 3 kW out there. The power density requirement is actually very high. It's more than 115 volt per cubic inch, because you need to put every power supply unit attaching to the server. And for the rack level, the power density requirement is a little bit lower, but the power requirement is actually more than 4 kilowatt and above. Normally we see 5 kilowatt and beyond. But power density can be a little bit lower requirement for 100 watt per cubic inch. But we still need to carefully design it to make this kind of power density requirement. Let's get back to the efficiency. You can see if we consider 97% efficiency for overall PSU, which means for 2 kilowatt PSU at half load, meaning 1 kilowatt operation, you only have 30 watt total loss for the entire stage. So you have to design your converter as as efficient as possible. Normally, the distribution is like on the AC/DC side, you want to design the PSU to be 99% efficiency, half load efficiency, and 98% half load efficiency on the DC/DC stage, which means you only have 10 watt total margin on your AC/DC stage. This is very, not that easy to meet. That's why we need to explore different topologies and different devices, especially when we have wideband devices, wideband gap devices, single hub and gallium nitride devices out there. So we can do this kind of better design to meet this requirement. So that's why today I will focus on this stage first, and then I will also then cover the auxiliary power stage. That's another stage we believe GaN will have very good value and will save the improve your efficiency and meet the titanium grade as well. Okay, let's talk about AC/DC stage first. For AC/DC stage or the PFC stage, there are two major functions from basic. Like you need to do two things. One is like you need to change the polarity from two polarity to one polarity. Another is like you need to regulate the voltage from the sinusoidal wave to a constant DC wave, DC level. So traditional PFC is a very good example of these two functions. It has a bridgeless, it has a diode bridge right after the input of AC, and to change the polarity of the input voltage, and then it will go through a boost converter. It has the active FET on the low side and the diode on the high side. This kind of asynchronized boost converter to do the voltage regulate, so that your AC input will be regulated to a constant DC output. Why we want boost converter? First is like, you know, the voltage. Sinusoid, it will get to close zero. So you can, with the booster, you always get to a constant higher level. So that's possible with boost. Another is like for the boost converter, your input current is continuous. It's continuous, and so that you can regulate this kind of current better. The issue with this kind of traditional diode bridge approach is actually with the conduction loss of this diode. You can see a very fast comparison below. At 10 ampere, if you have a diode, the voltage drop is around 1.3 volts, and that's 13 watt conduction loss total. But if you have a MOSFET instead of diode, the conduction loss is only 5 watt in this case. So the diode bridge itself will generate a lot of loss when you go to higher power. That's why when we want to push the efficiency, we definitely do not want this kind of diode in the circuit. So on the right-hand side is actually a kind of a variation of the traditional boost PFC. It uses semi-bridgeless dual boost PFC. It's kind of interleaving there to eliminate some of the diode, but the diode is still conducting and generating a lot of loss. So one straightforward way to improve that is actually, as shown here, the active bridge PFC. You have silicon MOSFET on the input bridgeless side to replace all the diode instead of to replace all the diode. In that case, you can change from the diode conducting to the MOSFET unconducting. However, your conduction loss of your MOSFET cannot be zero, and you still have this fast diode out there. And also this will be very, cost ineffective. You have 4 additional MOSFET there. On the other hand, so the price is some kind of issue with this one. Together with the performance side is not that good. On the other hand side, there are 2 bridgeless topologies. The first one is AC switch PFC. You see on these 2 topologies, there's no this kind of input diode bridge anymore. The first one is AC switch PFC. Although the input diode is eliminated, but during your operation, you can see on time there's only 2 MOSFET, but during your off time, there's still 1 fast diode and 1 slow diode, in the conduction path. And in the middle of here, two-node PFC is actually the topology. A lot of new designs are using these days because there is no diode conducting because the operation principle of two-node is actually it has 1 half bridge with slow FET, another half bridge with faster FET, with the faster FET. So the slow FET stage will use to change the polarities, while your fast switching FET is used to do the voltage regulation. Why this kind of two-node PFC is not suitable, it's not like the mainstream in the market before, it's because when you form the fast switches in this kind of half bridge, the reverse recovery is something you need to consider. for silicon device, this kind of reverse recovery is very huge, and also the COS loss. So it's not good to put silicon devices into a symmetrical half bridge and to do synchronized boost operation. But since it's different when you have silicon carbide and GaN devices, especially for GaN devices, there's nobody there, so there's no reverse recovery at all in this kind of tunable PFC operation. That's why we're seeing like GaN PFC, tunable PFC and GaN devices, they are like helping each other to get attentions and get design in this higher efficiency power supply unit PFCs. Next, I will going to show a more detailed comparison here and give you a better expression of why we think GaN is GaN plus tunable PFC can help you there on the PFC stage. You can see this is a case study we're doing 5 major topologies, including the classic boost with bridge rectifier. This is will serve as a benchmark. And then we have the classic boost with active bridge and AC switch PFC, tunable PFC with passive switches, passive diode, and tunable PFC with active MOSFET. The calculation of IM current and average current can be found here. So this is more like to show how we calculate the losses and do this kind of comparison. On top of this loss efficiency performance, we also compare the cost among different topologies. You can see we also list like the key component in each of the topologies and use the price there to do the to do the comparison of the cost. This slide is showing a 1.4 kilowatt case. As I said, the silicon MOSFET with diode bridge and classic boost PFC is shown here. And if we use that as a baseline on the efficiency, by changing from the diode to active bridge, you can save improve your efficiency performance to around 0.5% at half load. And by using the silicon MOSFET with AC switch boost, however, the cost of the active FET is very large, as I mentioned. If you consider the AC switch bridgeless PFC, the efficiency improvement is a little bit lower, but it's still considerable. Right now we are looking for a 1% efficiency, 1% loss target at the moment. So 0.3% improvement is already very large. And the cost is considerable low. Similar performance you can get with the tunable PFC with diode on the slow FET side. The cost is also around the same as AC switch bridgeless PFC. If you really want to design titanium grade, it's definitely better to maximize your efficiency performance. That's why you can see on the tunable PFC, the tunable bridgeless PFC with gallium nitride device and silicon MOSFET, you can realize a 0.6% improvement. Although, and with a considerably acceptable price increase. Similar story you can see on the other power level. Here is the 2.8 kilowatt PFC system at half load efficiency. Tunable PFC can give you a 0.8% improvement with considerably a little bit higher cost, but I will talk about cost a little bit better in the following slides. So this is conclusion basically from this kind of study. So compare with AC switching topology to normal PFC with active slow FET can achieve higher efficiency with higher device costs. So if we really need this kind of titanium grade efficiency, gallium nitride with normal PFC is the only choice here. Talking about cost a little bit more, this is why we think this kind of investment is worth it. Considering a 4 kilowatt PFC, if you can improve its efficiency from 98% to 98.8% with this kind of bridgeless tunable PFC with GaN, you will only have a considerably small cost added per PSU. However, if you run it for, the total of that will be only $6.2K cost added in the data center. But if you consider a 100 megawatt data center for over 10 years operation, that's $7 million savings for this 0.8% efficiency gain with gallium nitride. So the gain is definitely worth the investment in this place. And let's talk about some breakdown of the device, breakdown of the loss in tunable PFC. Right now, the operation of tunable PFC, we are talking about the CCM operation. So I forgot to mention this part on the previous study, all based on continuous conduct mode PFC, which means that's hard switching. There are also other like switching mode PFCs, like the CRM or ITCM. Like there's some other topology I will talk about later. Other operation state I will talk about later. So in CCM PFC operation, the major losses, device losses, come from these three different aspects: the turn-on loss, turn-off loss, and dead time loss. This is the switching losses. So turn-on loss is actually including the COSS loss, the overlap loss, and the reverse recovery loss. For turn-off loss, that's only overlap losses. And then the last part is dead time loss. With GaN devices, actually you can minimize all of them. You can minimize most of them with GaN devices. The COSS itself is very small because of the figure of my GaN is better. So the COSS is also smaller with the same adson. In that case, your COSS loss can be minimized. And GaN doesn't have any reverse recovery, so the reverse recovery side is 0. And considering the small CGD, CGD and QGD, CGD and QGD of GaN, the overlap loss can be minimized, especially with TI GaN. For our device, we are doing driver integrated. So all of our, when TI did our device, our concept is like we leverage our experience for the past couple of decades on the analog side, on the driver designs. We use all of these IPs together with our GaN technology development. We are doing this kind of driver integrated solution for all of our products. With this kind of driver integrated, we can minimize all the parasitic inductance of the circuit around the device, including the common source inductance and the driver loop, these kind of things. When the benefit of GaN is like you have very small parasitic so that you can switch it very fast. However, when you switch it fast, the parasitic is very big concerns to have a noise-free operation. By having this kind of integration, you can minimize the parasitic so that the switching speed can be pushed to the limit of GaN. At the same time, by having this kind of driver integrated, we can utilize the IPs we already have and put as much as many feature as we need into the device, like all these protection features and also the junction temperature report, these kind of things. So that's how TI we think that's the best device we are developing here. So by having this kind of driver integrated and you push the switching speed to the maximum, you can kind of lower the dead time loss as well, because you can minimize your dead time settings. Dead time loss is actually some kind of trade-off of GaN, because on one side, GaN doesn't have body out and there's no reverse recovery. On the other hand, the third quadrant conduct voltage drop is very large on GaN comparing with silicon and silicon carbide. So dead time loss can be large if you do not set the dead time very small. But with this kind of fast switching function, you can actually minimize your dead time loss. So in that case, TI GaN can help you to minimize all this kind of switching loss, so that that will help you push your converter to the highest efficiency target you want. Other than the performance-wise, as I mentioned, we have a lot of different features also integrated into our device. And these features are specifically targeting to help you design a more robust circuit or more robust PSU with TI GaN. I'm going to talk about them, some of the points here. The first one I want to talk about is actually the AC cycle drop. This is one requirement in many of the PFCO standard. Whichever is a rank level or is a ITE level, there's different standard out there based on different vendors. This kind of AC cycle drop test is required in most of the standard. Is like the device. So basically, the device, the PSU need to withstand this kind of AC line voltage losses half cycle. This kind of case. So in that case, the link with resulting in a very huge operating current for half a line cycle, this kind of 10 milliseconds. In most of the PSUs, we handle this kind of surge current by going into cycle by cycle over current protection operation. We only give the pulse to the active FET and use the other FET as the asynchronous rectifier to operate during this kind of surge event. But the issue, as I mentioned, for GaN, the third quadrant operation is a concern without state signal, because the voltage drop is large. In this kind of cycle by cycle over current protection operation, your asynchronous rectifier is actually doing that. If that's GaN, this transient thermal stress will be a concern. Even if you have built-in over temperature protection in your system, you will not be able to solve this thing, because this has happened when your device is off. For our GaN, actually, we integrated these kind of intelligent features. Our OTSD, this over thermal shutdown feature, has some intelligent functions inside it. It will also, we have the sensor to sense whether the device is working in the first quadrant or the third quadrant. And during the OTSD, if the sensor senses the device operating in first quadrant, it will shut the device down so that your loss will be minimized. This is easily understandable. And when it operates as third quadrant, actually the best way to lower the device loss is not turn off the device, but is to turn on the device. This is the intelligent features I'm talking about that's integrated into all of the devices. Like during OTSD, it senses in the third quadrant, it will automatically turn the device on, so that the device itself will be the loss of the device will be minimized so that this kind of operation will not result in thermal blow up. Here is some kind of here is a test result of this operation. For the diode side, for the passive switch side, we are giving it a low PWM all the time, so it serves as an asynchronous rectifier. When the thermal over thermal shutdown happens, you can see at the beginning it's still turned off, so it has this small dips there, and after that the device will automatically turn on itself, so to minimize the third quadrant loss there. So this behavior can mitigate the risk for thermal runaway and the device failure during this kind of operation. The second highlight here is our integrated short circuit protection. For our device, not only the overcurrent protection, but also the short circuit protection. The difference between them is the short circuit, we are not only monitoring the current level, but also monitoring the DIDT. When the device sends a higher DIDT than expected, it will go into this short circuit protection that will directly launch the cell in a shorter time and keep it, off for a longer time until you use the input signal to reset it or get the power up down. So having this kind of short circuit protection will help you to make sure, like, this is kind of additional insurance to your power supply unit operation. And on the other hand, it can also give you some convenience when you are in the design stage or in the test stage. So this will not blow your entire system off once it's into get into short circuit situation. Yeah, the last highlight I want to talk about is on the robotic stack is on our GaN qualification and reliability. This is some work TI has been doing it for years. So we not only followed the silicon related device qualification standard, they are also participant and participant in getting all this kind of standard and also followed all the standards to qualify our device. This standard will be specifically target of GaN devices, including the GaN long time reliability, the different mechanism of failure, and also the dynamic RDSR. So also inside TI, we have done the reliability test for a very, very long time. And the failure rate of our device is very small. The last thing I want to talk about is actually this search capability. A lot of people are saying like GaN device doesn't have avalanche, so that it will not survive in this kind of search cases. And there's some concerns from them because there's always some kind of search requirement for this different end equipment. But for GaN, although we do not have the avalanche, but GaN is handling this kind of search situation in a different way. All the GaN devices, they are designed based on have some margin. It will have some design margin when they're doing the device design. By having this margin, the transient over voltage of GaN is actually higher than its spec value. For example, 600 volt GaN devices. For our 600 volt GaN devices, we have the search over voltage capability up to 720 volt for the step voltage and 800 volt for the reigning. So this is a way for GaN to, as long as you can keep your link voltage below 720 volt during this surge, the GaN device can handle this kind of surge event. without any issue. This is a way for GaN to handle this search, so you do not need to worry about that. So there are definitely a lot more related things you want to learn, like we can talk about like the EMI design, like different control, this kind of work. We have no time to go into every detail, but you can refer to this kind of TI reference designs, PMP 23069. This is 3.6 kilowatt CCM to normal PFC. This is a typical system I was talking about. And it can realize a 98.7 peak efficiency, more than that, and for a very large power density. And you can go into the design files there to see how we are handling the other system level issues. Another example I want to show here is a different topology, a different variation in normal PFC. This is ITCM. We have a reference design done on that PMT 49888. So this 5 kilowatt what is ITCM? ITCM is basically a combination of CCM and CRM operation. It's a soft switching topology. I will talk about it in the next slide, but just a quick overview of this reference design result. You can see this is a 5 kilowatt design with two-phase interleaved ITCM. We can achieve more than 99% efficiency through a very large load range, and more than 99.2% at half load efficiency. So ITCM is the theory of ITCM is shown in here. So there are some pros and cons for CCM and TCM, CRM, PFC as I shown here. CCM is hard switching, but it has some benefit on the differential mode EMI design and also the control. On the other hand, CCM, PFC doesn't have any soft switching, so the density efficiency can be better. But the differential mode EMI will be a big issue, and also the large ripple. So for that, we have kind of using this ITCM approach. It uses additional RLC branch here to separate this kind of current into this LC is used to generate additional ripple on top of the CCM operation. So from the device side, you will see CRM, TCM-like operation, but from the LAN side, you will only see a CCM operation. So this is more like taking advantage of both both operations of the device side. There's no switching losses, but you at the same time you don't need a very large differential mode filter on the input side. For more details, you can go to this product page definitely and to see the details. The reason I want to highlight this one is also this is another unique feature of TI GaN. For this kind of TCM operation, you always need a sensing loop to sense when the current goes to zero. This is sensing. But when you do this kind of sense, you will have some delays inside it. Traditionally, we're using this kind of velocity coil or shunt resistor to do this kind of sensing, and it will introduce some kind of delays out there and result in the distortion. But for this reference design, actually we're using an advanced version of our device, this 3426 version. This is the ZVD function. ZVD function is basically, since our device, we have sensor to monitor whether the device is operating the first quadrant or third quadrant. ZVD signal is when the device turn on, it will sense whether the VDS across the device is positive or negative. If this is positive, the device will know, okay, this is a hard switching transient. And if this is negative, the device will know, okay, this is soft switching transient. When the device realized it gets a soft switching transient, it will send out this small pulse signal to the ZVD pin so that like you can the controller can know, okay, the device is already in soft switching. And if the controller doesn't get this signal, controller will know, okay, it's not in soft switching, so we need to adjust the timing to make it to be soft switching. This is a way we used to control in this reference design, and together with this advanced advanced version of our device. Compared with the traditional approach, there will be no additional losses in the sensor. At the same time, the cost of it is very small. So this approach is kind of the best with our device. This is a test result of our ZVD. You can see in the soft switching cases, we force the current to be negative, and it will give this pulse. But if there's hard switching cases, there will be no pulse there. That's a better illustration of what is going on with this function. Okay, next I will talk about the GaN in auxiliary power supply. This is, auxiliary power supply is another, an important part in PSU. It normally gets the power from the DC link, this 400 volt, and get to the auxiliary power from 12 volt to 20 volt, and the power level is from 5 watt to 60 watt. So why we care about this part is because every kilowatt server PSU will have this kind of auxiliary power supply, and since we are talking about the extremely strict requirement on the efficiency, we need to maximize the efficiency of this stage as well, so that we can save the losses from it. For example, let's do a quick, just a quick calculation for 5 watt auxiliary power supply. Traditional, the traditional approach is only 85 to 88% efficiency, and if we can increase that from to 93% efficiency, that means 3 watt power savings from the auxiliary power. And if that's 2 kilowatt power supply, that means 0.3% increase for the half range load. You see, this is another 0.3% is very important. Since we are talking about 1% loss here. So traditional way of doing that is, this is kind of flyback range, but flyback, there are many advanced version of it. Traditional passive clamp flyback, and these days we also have the quasi-resonant flyback. Even going further, the active clamp flyback. Quasi-resonant flyback is Rayleigh switching, so it still has some switching losses. And active clamp flyback is the soft switching topology. And for this study, I want to show the benefits of choosing GaN here. So we have the study with putting silicon in each of the traditional flyback, and then use GaN. We have 2 proposals. One is using our GaN in quasi-resonant flyback. Another is using our GaN in active clamp flyback. We make these kind of 70 cases to do the cost and the efficiency comparison. And on the secondary side, both DELT and SR FET are also considered into the comparison. So you can clearly show if we want to get better efficiency design, what kind of things which choice we should make there. This is a specification we used in this in this comparison study. 45 watt input-output range, and we fixed the switching frequency and the inductor. Actually, for GaN, we are even pushing for a higher switching frequency, like 300 kilohertz. But right now, let's just do an apple-to-apple comparison, and you can already see the value of GaN there. Here is the silicon and the GaN MOSFET we're comparing. silicon FET is a 450 milliohm silicon, and GaN is our TI2 TI GaN devices. The 3626, this is a single FET, and the 2610, this is a hybrid GaN FET with driver integrated. On the secondary side, the silicon short gate diode plus TI silicon MOSFET. This slide shows the major sources of the loss we are considering. On the device side, it's majorly the conduction loss and switching losses. For the turn-on losses, it's very high in DCM flyback, but it's medium in QR because it's doing the soft switch, it's doing the relay switching, and it's zero in ACF because this is soft switching. All the other component you can see we also considered into the study. Here is the result. For the traditional silicon DCM flyback operation, this is used as benchmark. The loss of it can be up to 5.5 watts. If you can switch that to QR GaN with the diode on the other side, you can save around 0.7 watts loss there. And if you're using ISR, that is further reduction of your losses. You can achieve around like more than 2 watt loss savings there. As I mentioned here, 1 watt of power loss saving is 0.1% half load efficiency improvement in 2 kilowatt PSU. So 2 watt loss saving is already very critical there. If you really want to squeeze every efficiency, squeeze every loss sources, ACF is definitely the best to go with our half-bridge solution. You can realize less than half of your total loss comparing with the benchmark, but also on the other side, the cost is also considerably higher. So from the cost side, this is a cost comparison. You can see the QR is not a that expensive solution as well. So you can based on your budget and choose the best candidate here. As I mentioned, if you want to push for higher switching frequency, you can see even more values from GaN. This is a case study. If you go to 300 kilohertz, both the QR and ACF will give you even better performance there. And with this kind of increase of switching frequency, you can have the cost benefit on your passive component like the inductor at the same time. Here is a reference design from TI on this auxiliary power supply side. This is 45 watt solar auxiliary power supply with ACF PMP23146. If you're interested, you can go to there and see the form factor and how we realize this peak efficiency, more than 92% peak efficiency with this kind of design. Okay, that's all right. That's it for my presentation. Thank you so much for attending this session, and hopefully you got what you need from the presentation. And feel free to contact us in terms of future questions or other things needed from us. Thank you so much.